Okay, so we have talked a little bit about gravitational potential energy. This is our expression for gravitational potential energy. What I want to do now is look at problems where I can apply conservation of energy. Energy is going to be conserved when objects are under the influence of the gravitational force only. And so we want to talk a little bit about energetics. And there's a lot to this, but we're just going to say a few things about energy and how we can apply conservation of energy in these kind of problems. So we know that the total energy of a system can be written, or I should say the total mechanical energy of the system, can be written as the kinetic energy K plus the potential energy U. What does it mean if the total energy is zero? What does it mean if this is zero? For an object, for example, near a planet. Okay. Consider the potential energy between the planet of radius r sub p. I drew that too small, sorry. And some object here. What can we say? What are a few things we can say? Well, one of the things I can do is plot the potential energy as a function of distance. And if we plot this equation as a function of distance, it looks like this. Because of this, the finite size of the planet, this is the source, let's say, of the gravitational field. There's a point where you actually cannot go inside the radius, and so I put this border around. So let's say the total energy is given by some value here, less than zero. Then the particle, or the mass, is going to be bound between these 2 points. Can't go inside the planet, and it can't go beyond this point. So this is E less than zero. So the particle is bound. What that means then is the kinetic energy is less than the potential energy. I'm sorry. The magnitude of the kinetic energy is less than the magnitude of the potential energy, and so it is less than zero. So the particle is bound between those 2 points. If the total energy is equal to zero or greater than zero, then the planet or the object, or whatever you want to call it, can have any value of x, or if we call this r, any value of r. And so it's unbound. So for any particle where the energy is greater than or equal to zero, it's unbounded. It can be anywhere, essentially. They go all the way up to infinity, so we call them unbounded. But if we're less than zero, then the motion is bound. Now, one thing I don't like about this graph that I've shown you here, it really assumes that this is stationary. In real life, this is not stationary. This is free to move, just like this object. And so it becomes more mathematically complicated to draw the potential energy. To actually analyze the system, you got to think of the full range of motion in 3 dimensions when this object is free to move. Now, this graph is also valid if the mass of this object, we'll call M1, is much greater than the mass of this object, and we think of it as stationary. But if they're moving relative to each other, I need to take into account the relative motion. And when we have those situations, we have to actually look at the problem from the center of mass frame. So we can transform the problem involving the relative motion of these two objects into the center of mass frame. I'm not going to go through that, but I want to tell you what the results are when you transform into the center of mass frame. Now remember, in the center of mass frame, the center of mass just moves at constant velocity, the momentum is conserved. But this looks different in the center of mass frame for a two-body system. It actually looks like the following. So in the center of mass frame, where these objects really are moving relative to each other, U looks more like this. And this is really, I want to call it the effective potential energy. It has more of this form, where U effective includes the gravitational term, and some other term, which involves the angular momentum squared divided by 2. And it's really the effective mass of these two. And I'm going to use the Greek letter U times R squared. Okay. So the potential energy has more, it really looks like this in the center of mass frame. If we transform the center of mass frame, the potential energy has a form like this. These terms both have potential, both have these dimensions of energy. And so we have an effective potential energy that looks like this. And this is what happens, for example, when you look at the relative motion between the Earth and the Sun. And when you analyze the problem from the center of mass frame, you get a potential energy that looks like that. And writing it this way takes into account the fact that these objects are moving in 3D. So now, if you have an object like the Earth, a planet like the Earth, and it has this much energy, then the motion of that planet is bound between these two values. If you have another planet that's orbiting the Sun that has this much energy, there's only one possible value for R. That means that that orbit is going to be a circle. In fact, any energy between is bigger than the bottom value and up to here, the orbit is going to be elliptical. If the total energy is 0, the orbit would be parabolic, and above 0 would be hyperbolic. But again, if E is bigger than 0, it's unbound. If E is less than 0, the motion of, let's say, the planet orbiting, let's say, the Sun or whatever it's orbiting, is going to be bound. You can also apply this idea to studying molecules. One interesting molecule to study, probably the simplest molecule in nature, is two hydrogen atoms together, basically bound together with one of the electrons removed. It's called H2+ molecule. And if you model the potential energy between the two protons are actually sharing an electron between them. Looks like this. Okay? It looks just like this, in this form. And the motion of the two protons is bound as long as the energy is below this horizontal line. This energy is required to go from the bottom here to the point where they're not bound, this energy, for a molecule that's called dissociation energy, which if you've had chemistry, you probably talked about. The other difference here, when we talk about H2 plus molecule, the force we're talking about is the electric force, not the gravitational force. Okay. When these energy level diagrams come in, again, they're important and help us to understand various physical systems. Okay. Suppose we have a rocket that's launched, let's say, off planet Earth, such that its total energy is E1. Okay. What does that mean? So let's say we launch an object off the Earth with some velocity. So the total energy is E1. How fast is it going when it's at a certain distance, R1, from the center of the Earth? Let's say when it's over here. The distance from the object to the center of the Earth is R1. Okay. I should grab my key now. So, we can say, what is the velocity at this location? Well, my total initial energy is E1. My total final energy is also E1, and it consists of kinetic energy plus gravitational potential energy. We bring this to the other side. Multiply both sides by 2. I'm going to divide both sides by m, and then take the square root. And that gives me the speed when it gets up to this point, R1. That's using conservation of energy, like we did in chapter 8 of our textbook when we talked about conservation of energy. The only difference is that here, G varies, okay, whereas it didn't earlier in the semester. What does it take to launch something off the Earth so that it escapes its gravitational pull? In other words, at what speed should I launch the object off the surface of the Earth so that it barely gets to infinity? Because when it gets to infinity, essentially the object has escaped the Earth's gravitational field. Well, the minimum energy is such that the velocity is 0 when it gets to infinity. Well, what's the potential energy when it gets to infinity? It's 0. What's the velocity when it gets to infinity? It's 0. So what we want is we want to figure out what velocity I should launch the object at so that the total energy is 0. Okay. I want to figure out what velocity I should launch my object so that the total energy is 0. That's really what I want to figure out because, again, the potential energy is 0 to infinity, the velocity will be 0 to infinity. So we want E total to be 0. And so we're going to have our initial velocity plus our initial gravitational energy. This r is the radius of the Earth. I can put r sub b to make it clear that this is the radius of the Earth. Goal is to solve for the initial of v null. Okay, so I set both sides. I move this to the other side of the equation. The m's cancel. I multiply both sides by 2. And then I get the square root. And I get that. So that's my expression for the escape velocity. Again, what this represents is I want to launch the object so that it barely gets to infinity. That means that at infinity potential energy is 0. So on this side, this is the initial energy. The final energy is 0 to 0. The final kinetic energy is 0. The final potential energy is 0. I want to launch it so my total energy is 0. And if you put in g, the mass of the Earth, and the radius of the Earth, this is about 11.2 kilometers per second, which is pretty fast. You have to launch the object up to a very high speed to get it to escape the Earth's gravitational field. Of course, you have to take into account, too, the fact that there's air resistance, etc. So this would be the minimum velocity. Assuming there's no air resistance. Now, another question we can ask is also, what should the speed be in a circular orbit? So we're going to get to that in a moment. But let's put in some numbers. And I made up some fun numbers because I don't want to use the large numbers like 6.67 times 10 minus 11 for g. And so let's pretend we're in a different universe, my universe, where g is 10 Newton meters squared per kilogram squared. And the radius of the planet we're trying to escape, the miniature planet in our universe, is 1 meter. And the mass of this planet is 10 kilograms. What is the escape velocity? What was the plug in numbers? The square root of 2 times 10 Newton meters squared per kilogram squared, and the mass of 10 kilograms. Divided by the radius of the Earth. Or, I'm sorry, not the Earth, but our planet. This ends up being the square root of 200. And the square root of 200 is 14.1. This would be the escape velocity from our imaginary planet, from our imaginary universe. Okay? Now, what about a planetary object that's orbiting, let's say, the sun, or a satellite orbiting the Earth? And let's assume that the orbit's circular. How fast is it going? Well, if an object's going in a circle, it has an acceleration. It's a centripetal acceleration. It's going in a circle at a constant speed. And it's undergoing this centripetal acceleration. And so, what's causing the centripetal acceleration? Well, it's the gravitational force. So we can set the gravitational force equal to ma, but a in this case is v squared over r. The cause of the force is the gravitational force. The result is ma, but in this case a is v squared over r. And so we can readily solve for the speed of the planet orbiting the sun or a satellite orbiting the Earth, the moon orbiting the Earth. So let's do that. Let's solve for v. It's a simple manipulation. I expect you to be able to derive this in an exam because it's pretty straightforward. I set the gravitational force. This is the big M is the object that we're orbiting, equals to ma. A is v squared over r. And I just need to solve for v. The mass of the planet or the satellite disappears, and one of the r's cancels. And when I solve this for v, I get the square root of the gravitational constant, the mass of the body that's being orbited, and r, the radius of the orbit. And what you see is there's a unique value of v for every value of r. Okay, one value for every value of r, there's only one value of v. And so this is how you calculate the velocity of an object going in a circular orbit. Could be a satellite, like I said, it could be a satellite going around the Earth, the moon going around the Earth, the planet going around the sun, a comet going, well, comets usually have eccentric orbits. Now, let's talk about orbital energies. For example, the Earth going around the sun. What is the energy of the Earth going around the sun? Well, its total energy is kinetic plus potential. So orbital energy can be written in the following way. M again is the object is the body that you're orbiting. And little m is the one that's moving in the path, for example, like a circular path. If it's going in a circle, then we can take this value of v and stick it into this equation, and we get the following. Now if I square that, I'm going to get g big N over r. What you notice is that these will subtract very easily. They both have the same denominator. They should have the same denominator. I love them. Do a good job with that. Okay. Actually, I should write the r so I can get there. Sorry about that. Okay. Let me make the r the same as that one. Now, when I subtract them, what do I get? I get that my total energy is half my potential energy. That's really a consequence of the fact that we are dealing with a 1 over r squared force and 1 over r potential energy. That's a consequence of that. So this is always true, that the total energy is half the potential energy. And this is true whether the orbit is circular or elliptical. Actually, it's for any type of orbit. I don't expect you to memorize this. I expect you to be able to derive this, because that's all I had to do. You can use this as a checkpoint to see whether your calculations are correct. Now, if the orbit is elliptical, A is the length of the semi-major axis of the ellipse. And again, the fact that the total energy is half the potential energy is a consequence of the fact that the force depends on 1 over r squared. Now, let's go back into my universe. This is the energy for a circular orbit, or elliptical orbit. Okay. This is my velocity for an object going in a circular path. Let's say we are back in my universe and we are orbiting a planet whose mass is 10 kilograms. The radius of the planet is 1 meter, but the radius of the orbit is 4 meters. The r here and the r here are different than the r in the escape velocity equation. This is the radius of the orbit. In the equation I had for the escape velocity, this is the radius of the planet you're trying to escape. That's the radius of the orbit. And so you have 2 r's in this problem. The r that I want is the 4 meters. Okay? So if I want to find the velocity for an orbit that's 4 meters in my universe, I'm going to put g as 10 Newton meter squared per kilogram squared. And the mass of the planet divided by the radius of the orbit. 10 times 10 is 100. 100 divided by 4 is 25. The square root of 25 is 5. And obviously, this is way less than the real case when for example, satellite orbits the Earth. We're talking about thousands of meters per second. Now, what is the total energy for this orbit? In my weird universe, well, my g is 10. The mass of the planet is 10. But I didn't give you the mass of my vehicle that's orbiting the planet in my weird universe. I'm just going to leave it there. And then the radius of the orbit is 4 meters. So what do we get from this? 10 times 10 is 100. 100 divided by 4 is 25. 25 times a half is 12 and a half. And if we make the mass 2 kilograms, then this would be minus 25 joules. That's how you do the calculation. I know these are weird made-up numbers. And then, like I said, I made up these weird numbers because the numbers are smaller than we raise the calculator. So at least you get to see how the equations work. What happens if we increase or decrease the speed? Well, if we increase or decrease the speed, we change R. If we increase or decrease the speed, we change the total energy. Okay, so basically, what happens is if you have a fixed orbit, energy is conserved in that orbit. No matter where you are in the orbit, the energy is the same. If you change R, you have to change the energy of the system. You have to change the kinetic energy and the potential energy. And that's going to allow you to find a new R and V. So to change orbits, you need to change energy. So to change orbits, you've got to change total energy. So for example, if your initial energy is K1 plus U1, and you want to change to a different orbit, then delta E, which is E2 minus E1, is got to be equal to K2 plus U2 minus K1 plus U1, which is the same thing as delta K with delta U. Okay? Now, in the case of gravitational problem, then this ends up being the following. Change in kinetic energy is this first term, and then a change in gravitational potential energy and the velocities can be gotten from the fact that they're going in a circle. So we can actually solve here for V1 in terms of R1, or we can solve it for V2 in terms of R2 and put it here. We can calculate the change in energy that's required to go from one orbit to the next. Now there's a little bit more to that than this, because we can talk about what is the most efficient way to go from one orbit to the next. We can do all those calculations. I mean, what can do those calculations? We don't have time to talk about that here. That's going to depend on which direction the object is going etc. But in the problems we're going to be doing in the homework, we're just going to be really focusing on calculating the changes in energy. What is the change in energy that's required to go from one orbit to the next? Now, this idea also applies to the case when you look at the electron in an atom. We have an electron in an atom, and you want it to go from one orbit to the next. You're essentially doing the same thing as you are here. You're changing your R and your V. Not quite like that, but that's what you're kind of what you're doing. Okay. Using a classical model, you could say that, but not using a quantum model. So you're changing an orbit from one value to the other. You're changing the electrical potential energy, and you're changing the kinetic energy of the electron. Okay, and so you can calculate how much energy is required. So how do you do that? Well, in the case of an electron in an atom, you can shine light on it, and you can make the electron jump from one level to another. In the case of, let's say, a satellite orbiting the Earth, one of the ways to do it is to do a burn. Basically, you're changing the internal, you're converting the internal energy of your rocket into mechanical energy. You do a burn. Okay, you burn some fuel. And there's a lot more than this because, like I said before, we can talk about what's the most efficient way to transfer from one orbit to the next. And there's one of the problems in the book kind of goes over that. But it can be an elaborate calculation. We're not going to